Hello, everyone. Welcome back to another Flan Talk. Today we have Sunny. She's a graduate student at Harvard who's very interested in the role of data in machine learning and mechanistic interpretability as well. And today she's going to give us a little talk about that. So take it off.
All right, cool. Well, thanks for inviting me to the talk. Today, I will be mostly talking about this paper called Data Drives Unstable Hierarchical Generalization in Language Models. And this is collaboration with Naomi Safra and David Alvarez-Melis. I will just get started. Also, feel free to ask any questions along the way. Okay, cool. So let's start it a bit on an overview and motivation of this work. So I've highlighted three parts in the title, and I will go over why I think all these parts are pretty interesting to me. So first is hierarchical generalization. I think about this as a special case study for out of distribution generalization because compared to other kind of OOD studies, we're focused more on algorithmic tasks. We're actually looking at the syntactic structure, which kind of has this hierarchical nature. So that's the first aspect, which I think would be very interesting to the community who study OOD behaviors. And the focus of data is that often we know that data is just so important for any models in general. But when you look at data sets in the wild, it's really to characterize the complexity and diversity of data. But when we are working on this more like synthetic setup, we can actually come up with very precise measures about what is the diversity and complexity for a given data set. And in those controlled study, we can kind of draw this connection about how data kind of shapes different out of distribution behaviors. And finally, what I thought it would be interesting is this like instability, which kind of touches on training dynamics. So in this work, we're drawing this connection between training dynamics and random variation. So when I talk about random variation, it touches on how models trained on different seeds can actually exhibit different training outcomes. So this kind of random variation are actually observed in language models. So in this case study, we're trying to make the argument that there's a connection between training dynamics and the training outcome. So this is kind of like the three parts of this study. Okay, so in terms of the talk outline, I will first give a very brief background overview on context-free grammar and the two case studies people use to understand how a model can form an internal representation of these grammatical structures. And after that, I will talk about the four key factors that give this inductive bias towards the hierarchical generalization. And the four key factors are the model architecture design, the data complexity and diversity, training dynamics, and also the loss function or the training objective. So after so far we will be sticking to this synthetic setting, but you might ask, why do I care about these synthetic language tasks? And in the extension, I will actually tell you that this kind of random variation and this bimodal distribution in models like performance clustering is actually observed in language models. So that's kind of like an overview of the talk. Okay, cool. So let's first look at the data generation process. Uh, I feel like before looking at these linguistic stuff, I often think about these synthetic tasks about sparse parity, or I think about counting tasks, which everything has this Markovian nature. But actually, to my surprise, when I look at English syntax, when you kind of think in the framework of context-free grammar, it's also surprisingly has this Markovian and hierarchical nature. So let's go through this example to build this sentence. My unicorn that doesn't sing does smile, which is kind of a funny, silly sentence. But so how do we form an English sentence like that? So there are a couple building blocks. So the first building block is you need to start with some hierarchical syntactic rules. So by syntactic rules, really mean that when you have a verb, it needs to follow by an object, and it's hierarchical in the following sense. So we usually start from a starting note, and then it will split into a noun phrase and a verb phrase. So here is an illustration. And after that, you have this noun phrase and verb phrase. So what happens after? For the noun phrase, it can be split into a determiner. So like the, those, and then the noun, so the unicorn, the elephant, and then sometimes you can even have a relative clause, which kind of like modifies the noun. Uh, and then the same as the verb phrase, you can be split into an auxiliary and the actual verb. So this is just one example of how you can start from these hierarchical structures, and then by splitting to different notes, eventually you get into the leaf note, which is usually the vocabulary, and then you build a sentence. My unicorn that doesn't sing does smile. So if you start looking at English syntax from this algorithm perspective, it actually is a very interesting case study to understand how models form these internal structures to really understand the data generation process of English. And we just given example. We have just given example of one sentence, but overall, to like build up this context-free English data set, you also have sampling probabilities of how different tree nodes have different likelihood of appearing in like a text corpora. Okay, and so now we know kind of how we can see like English syntax at this hierarchical tree. So how do models really understand English when they train on these hundreds of thousands of English texts? And do they really understand English grammar? In order to kind of probe a model behavior, there are kind of very clever case studies that we can do. So I'm just going to give example of two tasks, which I will most be focusing on throughout the talk. But you can kind of infer that there are similar ways to do the same thing, but kind of really in the same flavor. So the two tasks are question formation and tense inflection. So usually for those two tasks, there are two solving strategies. The first is a linear rule, or you can think about as a simple heuristic. So let me just demonstrate with example of question formation. So if you have a linear model, you start with a sentence, my unicorn does smile. The linear rule would just move the first auxiliary does to the front of the sentence. However, if you kind of use this kind of simple heuristic and test on the out of distribution sentence, which is the sentence below, you can see that if you always just move the first appearance of do, does, doesn't, don't, you will just fail the task at the bottom line. So that's kind of like the simple heuristic. So in contrast, we also have the hierarchical rule, which kind of really requires the model to understand the underlying data generation process, not just like the Bayesian probabilistic modeling of the kind of like the surface level statistics. So here you can see that if the model really forms this internal tree structure, then both the in distribution and out of distribution task can succeed. So I'm kind of hinting that there is an in distribution and out of distribution test. So indeed, how we probe the model's understanding of this data generation process is actually trained on the ambiguous data. So when I say ambiguous, it means that both the linear and hierarchical rules can solve the task. So it's really always the first case here. And then so you'd ask, should we even expect model to like generalize out distribution if all it sees are like examples where it can be solved by the linear rule? So that's kind of really the point of the test here is that the model can only solve those out of distribution tasks if and only if it kind of forms a hierarchical understanding of English syntax. So that is a basic setup. So yeah, so here comes the question: when do models generalize hierarchically? So there are actually four key factors that can induce this kind of out of distribution generalization. So architecture does matter, and how you train the models also matter. So the loss function, but the kind of the data also matters. And finally, even if you have all three, I will show you that having all three components does not guarantee you this kind of generalization behavior because there's also this training dynamics piece. So I will kind of go over the four factors one by one. So let's start from the model architecture design. So this is kind of the work from McCoy, Frank, and Linson from 2018. So yeah, so let's look at if different model architecture design can lead to a model to generalize hierarchically. So in their experiment, they trained on three recurrent neural network-based encoder-decoder models. So without going into too details, so the SRN is like the very naive, simple recurrent neural network design. And then they also have this gated recurrent unit, which kind of already tries to have this hierarchical inductive bias built into the architecture. And then finally, back in 2018, they still used LSTM. And then in all three architectures, they also try to put this attention into this decoder. So by this attention, it's really kind of like the precursor of the transformer mechanism. But really, what they did is to allow the decoder to access the intermediate step of the encoder layers. So here is kind of their main experiment outcome. So let's just unpack this a little bit. So you can see that for out of distribution across the three models, the accuracy is quite different. So for example, out of distribution, the long LSTM basically have like zero accuracy, means that it's like purely, it just is not capable of this hierarchical generalization. Versus if you look at the gated recurrent unit, it can sometimes get it correct with 70% of accuracy. And then again, they also noticed that like the use of attention is quite important for a model to gain this this kind of hierarchical generalization behavior. So kind of maybe, yes, architecture matters, but none of this can do it perfectly. So even better, what they did is they designed a tree structured network, which is kind of like a weird design, but basically instead of having like these like standard architectures, they build this one that just like had this tree inductive bias into the design, and this is the encoder and decoder network. So by kind of like really just like inducing this inductive bias through this specific architecture, they did show that the tree and tree both having the tree structure in encoder and decoder can get you to like 99% of like generalization accuracy. Cool. So this is kind of like about like, yes, model architecture does matter. So is that all you need? So it turns out that training dynamics also matters. So this is the work from Sikor-Murty and other people called grokking of hierarchical structure in vanilla transformers in 2023. So yeah, previously we've only been talking about pretty ancient architectures. So obviously now we care more about transformers. So the question is, would transformers also have this kind of like hierarchical structure built into it? And their finding is that yes, transformers can also generalize hierarchically, but you need to train it for long enough. And that's kind of why like we are also tying this out of distribution to grokking. So in their plot, you can see that B and C are the question formation and tense inflection tasks I have introduced to you, but they also trained on Dike. But really, these have like a similar flavor. You have in domain, which has two ambiguous which is ambiguous because the both linear and hierarchical rule apply. But on the generalization set, it's only the hierarchical rule. And overall, they have observed that training would saturate on those in-distribution performance really fast. And to allow the model to grok hierarchically, you do need to allow the training to converge for a while, and then suddenly you will see the model would have this transition from the linear rule to the hierarchical rule. So let's unpack a little bit of why they call it structural grokking. So it's grokking because it's similar to all the other grokking tasks that there's this delay between trivial and non-trivial OOD performance. But it's not just grokking because in classic grokking, we usually train and test on the same in-distribution set. It's a matter of like, have you seen the data during the training? But you're really drawing from like the same sparse parity task. And in structural grokking, it's different from classical grokking in the sense that the model not only need to like stop memorizing training data. So that's the step number one. And the step number two is it needs to apply from a simple to a complex heuristic such that it can generalize to this outer distribution data. And so far we've seen that model architecture does matters, and transformers can generalize hierarchically, but only if you've trained long enough. But again, is it still sufficient? And I will next show that how you train the model, the loss function also matters. And this is called the learning syntax without planning trees from 2024. So in their experiment, they start training on decoder-only transformers. And they tried 4 different objectives. The first is the standard language modeling. So we train on the DEX token prediction task, where both the input and output are taking gradient of. And in contrast, you can also try prefix language modeling, sequence classification, close completion. So these are like other alternative of training on the same data set. And here is the outcome. So again, we can look at the question formation and tense inflection, but they also have other similar syntactic case studies. But really, the bottom line here is that language modeling, in other words, kind of next token prediction, is actually what you need to induce hierarchical generalization, because sequence to sequence modeling, prefix language modeling, classification, close completion, all these cannot consistently induce this hierarchical generalization. Kind of the intuition is that you really need to like learn to speak the whole sentence in order to like understand English grammar. If you're only training on like, like a classification task, then somehow it just doesn't work. Or for close completion, if you're just like completing certain pieces of the sentence, that's also not enough. So they concluded that the loss function, in other words, this language modeling, is a source of inductive bias for models to generalize hierarchically. Yes.
Yeah, I know this is in your paper, but I also read this a while ago and forgot. But can you remind me what prefix language modeling is? How is that different than normal language modeling?
Yeah. So in prefix language modeling, because in question formation tasks, they have a statement and and then a question. So it's kind of the encoder decoder, right? So your input on the statement, and then you output the question, and your gradients are only taken on the question part. Sorry, the question part.
I see. So it's just like
You mask the
the
first
gradient
half
for
of
something.
the input, yeah.
Got it.
And that's kind of saying that like only learning the questions is not sufficient. Somehow you also need to learn how to state a sentence so you can learn the hierarchical rule.
Sure. Thanks.
So that's kind of an overview of like 3 factors. But what about like data? Is it like if you have the correct model architecture and you start taking next token prediction, and you're good to go. So I will show that probably not, it wouldn't surprise you that data also matters quite a lot. But I think what's interesting here is that because we can really understand the data generation process of these context-free grammar, we can have this precise measure of what defines complexity and diversity in this data, and this draw this connection about how these characteristics of data really shapes models' outer distribution behavior. Let's first kind of get a primer on there's two types of embeddings in English grammar. So the first one is called center embedding, which kind of is this recursive and nested structure in English. And there's also this right branching, which follows this linear development in English. So maybe an example will kind of like explain a bit better. So right branching really refers to this like development that if you keep looking to the right of your sentence, it really just flows. So for example, my unicorn does entertain her trinosaurs. So center embedding, on the other hand, you have this relative clause that will just suddenly appear in the middle of your sentence. And it is not to, it kind of like interrupts this linear development of the sentence. So for example, here in red, who didn't wait, really refer back to this unicorn. And you can see that because you have these like relative clauses embedded in these like in different places in the sentence, it really kind of like gives the model a hint that English is truly hierarchical in nature. So with right branching sentences, for the model to predict this, it just need to use like a bigram model, right? You just need to know unicorn is a singular form, so I apply does. But if you keep this kind of linear bigram model, it's not going to be very good at modeling this kind of center embedded sentences because here the bigram model wouldn't point you to even anything. So you say, sure, the model can use a four-gram model, but then the catch is that relative clauses can be arbitrarily complex. So I think the intuition is that because of this nested structure, the model will eventually switch from this trigram, bigram modeling to this hierarchical representation of English syntax. And so why do these two things have very weird names? It's because linguists have actually been studying different types of English sentences for many years. And here I'm citing a paper from 1980 that for children to understand English grammar, we really rely on these center embedded sentences. And this is a very celebrated claim in linguistics. So does the model do kind of the same thing? So in our experiments, we found that both center embedding and right branching can exist in the training data. And what we do is we take subsets of the training data and see what if by training on subsets of them, what are the generalization outcomes. And then we can see that if we train on the original set, the model will have a strong bias to generalize hierarchically. But really, it's when you only train on the center embedded sentences, this inductive bias towards the hierarchical is very, very strong. Versus if you train on right branching sentences, the model just kind of would fail. This experiment really confirms that what makes human understand English language is also what makes models form this hierarchical representation of English grammar. But kind of when I was doing these experiments, I noticed that the outcome, which is random across 50 random seeds, is really not consistent. Sure, we can talk about like this has a strong inductive bias, but the outcome is not guaranteed. So I was curious to understand what was going on between different seeds. And this leads to the second part, which is understanding even we have the correct architecture, the correct data, why training dynamics still matter. So here I'm gonna define two characteristics of training dynamics. First is stability. So stability, I'm really talking about when you're looking at one seed, one model run, how does model perform across different steps or different epochs. And then when I talk about consistency, I'm talking about at a given point during training, I look at across different random seeds. Are models arriving at similar performance across different seeds? So really like stability talks about like one run and consistency talks about different runs. And here is a visualization of the training dynamics across 50 seeds. We use a learning rate decay. Note that I'm putting a log scale on the x-axis, which is the step. And then you can see that the loss function is very consistent across different seeds. And then the validation accuracy, which is the in distribution performance, is also fairly consistent. It's also stable because after the training has converged, it always reaches 100% accuracy. But in contrast, when you look at the generalization set, the performance is both inconsistent and unstable. So maybe before 10,000 steps, the performance is rather consistent across seeds. But after that, you can see this wild chaos of different model performances. So what is going on there? And how does it relate to the training outcome? So let's first come up with a metric to describe this chaotic behavior during training. So we use the standard signal processing notion of total variation to measure training stability. So if we define T as total training steps and small t as a checkpoint at a fixed interval, we can define total variation just as the absolute difference across training steps. And just to give you visualizations of different total variations. So for example, these runs have really small total variation as the stability metric versus these are the very like chaotic runs, which you would have much, much higher training instability. So now we have a definition of stability and consistency. We also define how we can measure stability. So we are ready to understand if there's this relation between training outcomes and training dynamics. So here's the experiment that we do. First of all, we know that center embedded sentences are very important for hierarchical generalization. So we are ready to define data complexity as the ratio of center embedded sentences in the training data. And we can now examine how data affects both stability and consistency. And here is the result. So across the 5 panels, we are varying the ratio of right branching sentences, which I denote as a percentage of linear. Linear meaning that these will induce linear rules. And on the y-axis, I'm looking at the total variation, which is a measure of training stability. And y-axis, I'm looking at generalization behavior. So this horseshoe-shaped curve across different data sets is telling me that there are 2 characteristics that affect whether a model can generalize hierarchically. First of all, you want to train on data that really induces the hierarchical rule. But second of all, if your training is very chaotic, if the model never learns to commit to the hierarchical heuristic, you will have this inconsistent outcome across seeds. And as your data becomes more homogeneous, either because of lots of linear inducing data, the yellow, or hierarchical inducing data, the teal, then more seeds becomes very stable. And stability really ties to learning either the hierarchical rule here or the linear rule here. And the effect of mixing training data is really to destabilize training. And the outcome of destabilized training is really this random variation across seeds. And interestingly, this horseshoe shape is really kind of the same across data mixes. So kind of in conclusion, data complexity drives training stability, And then at the second step, training stability really ties to learning the linear and hierarchical rule. So this is in the paper, I also study data diversity. And just really briefly, we have focused more on the y-axis here, which is data complexity. And we have shown that when you have purely hierarchical inducing data, you can have lots of very stable runs and have very consistent training outcomes. In contrast, if you have linear inducing data, but homogeneous linear inducing data, again, training is very stable and consistent. But you have this middle chaos region where when data becomes kind of like inhomogeneous, you have the most amount of random variation and inconsistent outcomes across seeds. So this is kind of like once you have this different data mixes. But we can also look at the y-axis, sorry, the x-axis, which measures data diversity. And then you can see that if your data is not diverse, which in the paper we measured by the number of unique syntactic structures, the model cannot consistently extrapolate any rules, and it actually becomes kind of stable. But it never really commits to the hierarchical rule. And in this middle regime, when data is mildly diverse, then you have this chaos and instability behavior. But this chaos and unstable behavior would again disappear once your data is diverse enough. So that's kind of like the full picture of the more synthetic setup. And we kind of have shown that you really need the four pieces for the model to generalize hierarchically. So so far, we've just kind of been looking at these like smaller language models trained from scratch on this context-free grammar. So does this kind of study matter? In other words, does this kind of data characteristics really impact training outcomes and random variations in real-world language models? So the answer is yes. And I will show you that, first of all, this kind of random variation across random seeds are actually observed in real language models. And the second is both data and model scale are very important in controlling those random variations. So this is kind of the concurrent work with my other collaborators. So the key question that we want to answer here is, would large language models trained on different data mixtures also exhibit inconsistent training outcomes? And in the next set of experiments, we unfreeze the last layer of Qwen 2.5 instruct models. And the point of unfreeze last layer is that in the ideal world, we want to train a bunch of large language models from scratch with different data mixtures, but it's a very expensive experiment. So really to simulate that kind of environment, we just unfreeze the last layer and do a continuous pre-training. And then for the data, we train out a mix of the MMLU training data and the C4 news data. So the point of having MMLU training data is to teach model how to perform multiple choices at the same time do this language inference tasks. And then the C4 news data is just a generic English modeling, maybe has a slight focus on like news kind of predictions. And the goal is to evaluate if the model can perform well on the MMLU benchmark. And here are the results. So let's first look at the left panel. So by unfreezing last layer, on the x-axis, I'm showing you how much MMLU training data I'm mixing in during training. On the y-axis, I'm showing you the test performance of the MMLU accuracy. And this is showing you that the same kind of bimodality is also observed in these language models. And across data mixtures, with 5% training MMLU training data, none of the models can achieve non-trivial performance on the MMLU benchmark. Versus if you increase the data ratio to 10%, some seeds might completely fail on the MLU benchmark, but some seeds can really start picking up this MMLU performance. But the interesting thing is that this distribution is quite bimodal. And as soon as you have 20% of MMLU training data, all 20 seeds can achieve above trivial performance on MMLU. And now let's fix the data ratio and observe the model scale. So that's the right panel. Previously, we have seen that 0.5B model on 10% of the data have this bimodal performance. But on the same training data, if you have a larger model, the model can actually all achieve non-trivial performance. So the intuition on scale is that given the same data mix, a 0.5B model might face this competition to I either have to learn to do MMLU or I have to learn to do the C4 news. So there's this circuit competition versus for the 1.5B model, because the model is much larger in scale, it can actually just pick up the MMLU from 20%, from 10% of the training data without sacrificing the C4 performance. So what kind of is the maybe like the lesson here from observing all these different model performances across random seeds? It's really this interpretation of emergence. So we will show that because model have this bimodality when you measure their performances. So by really sampling from like these bimodal distributions, you can either have a breakthrough moment, which is this kind of like emergence argument, or you can have a very linear improvement. So this is like give us a second thought on when people claiming that we have found an emergent behavior. Is it really because that it's truly emergent, or just because in those language model tasks we only train on one seed and they're just like this like bimodal distribution? So it depends on how unlucky or lucky you are. You either get an emergent behavior or linear behavior. Cool. So that's kind of the main points I want to talk about. So to conclude, we kind of started from this synthetic task of model English grammar, and we talked about how how all four factors are very important to induce hierarchical generalization. Specifically, there's this data complexity measure, the model architecture, training dynamics, and loss function. And then because in those synthetic settings, we can understand the data generation process. We can reason through what are really like the measures of data complexity and diversity. And then we were able to draw this connection of like how these two metric can drive different out of distribution behaviors. And then we kind of like switched to more real world settings, and we showed that in real language models, this random variation and bimodality is also observed. And because of this like interesting bimodal behavior across different model scales, sometimes we will observe an emergent behavior. Sometimes we'll observe a linear development. But it might just be because of the fact that we usually train on one random seed and not thinking about performance as a distribution. So really, maybe a lot of the emergence we're observing is just this mirage of random variations. So that's the end of my talk. Let me know if you have any questions.